Here we go. We're going to take a look at the Hextenna again. This time we're going to be looking at a 20-meter setup. And what brought this about was that our ham group had a photo activation at SB Elliott Park, and we were able to install the Hextenna on WN3V's mast. That got it up in the air 20 feet or so. And this was the first time we'd had the Hextenna up at an elevated position. We normally operate it on a tripod, which puts it about 5 feet above the ground. So since we had this opportunity, I went ahead and used a antenna analyzer and ran the test on this antenna up on the mast, and then ran it again with the same antenna sitting on the tripod so we could compare the two settings and see what the extra elevation might do for us. We used my Rig Expert AA54 and the companion software, and we'll get started here. A lot of times when you're working on an antenna or any kind of system, what you're often doing is trying to answer the question, well, what if I change this or that? And there are a variety of ways you can go about to answer that question. One is you can guess, I would guess. The other things you could do, one would be to use modeling, and this is used quite extensively from what I've seen in antenna design using finite element analysis, so that you could compare results of 2 or more modeling runs. Now, my experience with FEA modeling has been that, and most of my experience has been in modeling of heat transfer, fluid flow, structural members, those types of things, is that the absolute results are suspect. And the reason for that is particularly with the heat transfer and the fluid flow, the initial conditions needed to set that up a lot of time have to be estimated, because sometimes it's difficult to establish what the initial conditions for the model should be. So that puts a little uncertainty, in my opinion anyway, on the absolute results that you get. But what it can be used for, I found, is that it can be an incremental comparison where you do a run, a model run with a certain set of initial conditions, change one variable in that model, and run it again with the same set of initial conditions, and then compare the two, and you're looking at the incremental change. So that can be kind of useful. The other thing you can do is empirical testing, where you take a similar approach, where you have one set of conditions, you run the test, gather the data, and then adjust the system to the next condition that you want. In this case, we're going from a low elevation to a high elevation. Run the test and then compare them and see what you can determine from the analysis. You can do multiple changes to systems, but those usually require more tests and mathematical analysis, a little more rigorous, where you're using, say, factorial designs to do it properly. So this is going to be a simple 2-level test, and we'll see what we can dig out from the results of the analysis. So this is a graphic of the two setups. One is on the left is the Hextenna as we normally use it when we deploy our portable station, and it's got about a 5-foot high tripod and the 2 elements that are adjusted to a particular length to get us resonance at a pre-selected frequency. Works extremely well. We've had great success. And then on the group's POTA activation, like I mentioned, we were able to get it up on Mike's mast, up there 20 feet or so, and that's what we were looking at there. So I took the rig expert and we ran the 20 meters sweep while it was in this configuration, and then ran another 20 meter sweep here. And then we took a look at those two data sets with the Antenna Scope 2 software. So what we wanted to uh, ask or to understand is what changes would we see with the higher mass. And I just kind of mentioned this. I got ahead of myself as I usually do on the slides, but we're going to take a look at the 20 meter response with the antenna at those two different elevations. This is the standing wave ratio plot that the program generates, and you can see here we've got it set up at from 14 megahertz to 14.350, I think it is. That's kind of spot. Yeah, 14.350. And all of these, this slide and the following slides are arranged so that I have the Mast data on the top of the page and the tripod on the bottom of the page, and the frequency scales are the same, and the vertical scales, in this case SWR, are the same. So if we look at the SWR, when it's up on the mast, we have incredible, almost unity SWR through the whole frequency range. And then we start to come up here a little bit, but still, even at that, we're at about 1.25, which is an excellent SWR for receiving and transmitting. If you look at the results from the antenna on the tripod, we still have very good results, where here it looks like we're at about 1.6 SWR, and we go through the whole band below or at 2, which would be considered very usable antenna. So there is a difference in the SWR, where we improved the SWR by elevating it, and that's probably not unexpected. But then the question always comes back, well, what is it really going to get me? And that's what we hope to answer with the next couple of slides. So another plot that the software generates is the phase angle at each frequency. And we'll go back to the impedance triangle to remind you that I'm sure this is all on everybody's tip of their tongue. So something you check out every day. But the impedance triangle shows the relationship between the real resistance R in this diagram and the reactive capacity, or the reactance. And the reactance can either be inductive or capacitive. And then the vector sum of this resistance and the reactance gives you what's called the impedance. And the length of this vector here, the z vector, is the magnitude of the impedance. And we'll look at that a little later. So the impedance can be described as the magnitude z at an angle. In this case, it's phi. So what this is, we take a look here, we can see at 14 megahertz, the phase angle is 0. Now, what that means is that tells us quite a bit. One thing it tells us is that this angle being 0 means that the resistance and the magnitude of the impedance are going to be the same. This is the point where the reactive inductive reactance and the capacitive reactance cancel each other out, so there is no reactance. And if you recall from our studies on impedance and reactance, that's the point defined as resonance, where those two reactive values cancel out to 0. So this shows us where the resonant frequency is when it's up in the higher mast. And then you can see as the frequency increases, the reactance increases, the net reactance increases, and still stays, the phase angle stays pretty low through the whole band. Now, if we look at the same plot for the tripod mount, you can see 0 degrees is here, which is where we were at. The phase angle was 0 on the Mast of 14 megahertz, but here we're a little higher. We're probably, that may be 12 or 15 degrees. And as the frequency increases, then the phase angle decreases. So what's happening is this part of the triangle's getting smaller and smaller and smaller, shorter and shorter, until we get to this point where the reactive component goes to 0, which is what this phase angle's telling us right here. So this is the resonant point, resonant frequency for the same antenna when it's mounted on the tripod. Now, the thing that's interesting to note here is that you can see the resonant frequency is right about here, and yet on the same antenna, the elevation up higher, the resonant frequency is here, so it's a lower frequency. So we can see that one thing that happened while when we moved the antenna from the 5-foot to the elevated position, the resonant frequency moved down due to the height. Now, the best way I can describe that, and I may be wrong, if somebody knows for sure, let me know. But the way I look at it, when the antenna is close to the ground, you get more capacitive coupling of the antenna with the ground. So you have more reactance. And as you raise it up from the ground, the capacitive reactance gets less. So your resonant frequency moves down in frequency. So that moves, one of the reasons the shape of the curves was a little different on the standing wave ratio. So that's a look at that phase angle as we sweep through the 14 to 14.35 megahertz. Now we take a look at the up here, the red R is resistance. X is, I think that's an X. Yeah, it's an X. The green X is reactance, and the magnitude of Z is blue. So this is the magnitude of Z, the length of this vector. The reactance is the length of this vector, and the resistance is the length of this vector. Now, when we have the antenna up high, because the phase angle is 0 at the resonant frequency here, the reactance is 0. It's all pure resistance, and you can see how incredibly close this resistance is to, and the reactance, 250 ohms, which is characteristic impedance for the coax, and I believe pretty close to the characteristic impedance of free space. So this is the reason that the standing wave ratio was so low, meaning that we were getting very little, if much at all, reflected power back from the antenna. And you can see when we're on the tripod, the impedance, the blue line, is higher, and we have this reactance. We saw this on the phase angle, comes down here through the resonant frequency and then continues to drop, which causes the reactance, or the impedance, Z, the blue line, to increase because this part here is increasing. So not quite as good a impedance match through the system as at the tripod as we have on the Mast. So that was an interesting difference. The next plot that the software generates is based on a parallel model of the antenna, and I'm not too sure where you would use this or where it would be applicable. I think the series model is a pretty good model for a dipole, but I think this parallel model where instead of series elements of inductance and capacitance, we have parallel elements. Excuse me, might be a good model for the case of a multi-band antenna. And I could see where each band could be modeled as a parallel LC circuit, and there might be some things you can pick up if, say, if we were going from 10 to 40 meters. The sweep was through 3 bands, or several bands there actually, with the 12, 15, and 17. I don't know. This may be the best thing to look at. It may be something we'll try with a multi-band antenna and see how that works out. But the one thing that's noted, you can see this transition here on the reactance. It flips from high to low, so that resonant frequency is right here when we're on the mast, and we can see it's up higher, as we noted on the other plots on the tripod. And then the fourth plot that is generated is a value called return loss, and it's similar to standing wave ratio in that what it's doing is measuring the power of the reflected energy from the antenna. And calling it return loss, I think, to me, it's kind of bass backwards. It just doesn't make sense to me, but I understand what it is. If I just don't think too hard about what they call it. But this is a web page you can access that has a good treatment of return loss, explains it very well. In fact, this is where all this information came from. And you can see, for example, if we have a standing wave ratio, an infinite standing wave ratio, then the return loss is measured as 0 dB. And what that means, at 0 dB or infinite standing wave ratio, all the energy that we're sending down the transmission line to the antenna is reflected. Nothing at all is getting to the antenna. And then as the standing wave ratio improves, we get a little less reflected power. Say we go to 3 dB return loss, which is equivalent to a standing ratio of 6. Then we get a 50-50 split, excuse me, of reflected power and power to the antenna. So we continue to increase the standing wave or decrease the standing wave ratio number, and the return loss increases. And this gold band here kind of shows you at what dB reading you have, how much of the power is getting to the antenna. So if we take that and plot it against the return loss, we get this graph here. And you can see here, this is the return loss readings. And here we can see how much power is actually getting to the antenna. So that if you can get a return loss reading, say at 20 dB, you're getting 99% of the power to the antenna, with 1% or less being reflected back. So it's a way to quantify, in terms of power, what's coming back from the antenna and not being transmitted as a part of the signal. So we take a look at the fourth plot that we get off of that software, the return loss. And when we look at the mast, on this axis, this is the return loss readings from 0. This is 40 dB. I stuck 5 dB in here. And then I put the values for that decibel level of power getting to the antenna. So at 5 dB, it's 68%. If we're at 10, we get 90% to the antenna. 20 gives us 99. And if we're higher than that, we're going to get more than 99, but you ain't going to get more than 100. So it's you get very little change in the actual power to the antenna if you get much over 20 dB here. And we do the same scaling here on the tripod plot. And the thing to note here is that if you look at the tripod, this is the area, the frequency range that we want to operate. We're concerned about the general section of the single sideband for 20 meters. So here we have that when we're on the tripod, we're getting 90% of the power to the antenna, which isn't too bad, particularly for a mobile or a portable antenna. However, we take that same antenna and raise it up a bit, and we're getting well over 99%. Well, you can't have too much over 99%, but we're getting almost all the power to the antenna with very, very little, less than 1% reflecting back. So that's a good thing to know. So then you have to wonder, what is the best height to have that? Because we only took it the readings at two heights, the tripod and the mast. Got ahead of myself again. What's the best mast height? I probably could take that slide out. What this is a plot that I found that shows the gain of a dipole in using dBi, or decibel readings of an isotropic antenna. And they have three bands here. You can see they're all very close, 160, 80 meters, and 10 meters. And so the gain is shown here on the vertical axis. On the horizontal axis is the fraction of the full wavelength. So right here would be 0.1 lambda, or 0.1 of the wavelength of whatever the band you're looking at. Here would be a half wavelength, and then here would be a full wavelength above the ground. So you can see how that gain varies as we raise the antenna above the ground. So I was interested in the 20-meter dipole. It's not there, so I just kind of eyeballed the gain readings. It'd be in here between the 10 and the 80, and that's all pretty close. So I took the same wavelength plot here, the steps, which is that column there. And then I came over here and I wanted to figure out what the wavelength is of a 14.2875 megahertz signal. The reason I picked that is that was the targeted frequency that I was looking for when we tuned the Hextenna. And you go through a little number crunching there, and you find out that the wavelength for that frequency is about 68.8, 68.9 feet. So what I did is I took each one of these fractional values and multiply it times that 68.9, and that shows you the feet above ground that fractional wavelength is. So right here, 0.3 lambda, we're at 20.7 feet. So that's kind of where we were operating. And this was the gain, the isotropic antenna, and then I translated that with the 2.15 adjustment for dipole antenna, because I wanted to see the gains of the dipole. So what we end up with here is this little plot that shows us what the gain would be at different heights above the ground. So we get here, and we're right at about, this is where we operate on the tripod, and it's not showing too well compared to what we do if we can elevate it. We continue to increase the height, and we see at 15 feet we get up to about 3.5 dB. And then the thing we notice is that this thing not only flattens out, but it kind of dips down. You can kind of see that here and you don't start getting increased gain until you start getting close to 30 feet elevation. So the gain, from a gain standpoint, the antenna is going to be fairly the same through this range of heights. So when I looked at it, the issues associated with stabilizing a 30-foot, particularly portable mast, are a little more difficult than a 15-foot portable mast. So it looked to me like what we'd do is we'd just take work towards a 15-foot portable mast to put the antenna on if we want to use the elevated antenna. And I was thinking about using a fairly rigid mast with a drive-on type base that you can drive the car on and support the mast is a good way to implement that. So it's kind of what I talked about there in the gold box. So my conclusion is if I operate the Hextenna at about 15 feet above the ground, I should realize a pickup of a little under 3 dB. And that's it's that. I mean, we're doubling, since it's about 3 dB. We're doubling the power, which sounds like a lot, but if you look at it in the context of S units, there's a ratio of about 6 dB per S unit. So what this would really do is get us to pick up about a half an S unit on our transmissions. Now, the only place that really would make a difference is at a station where our signal was just, say, on the tripod. If our signal was at the noise level and couldn't be copied, if we had the elevated mast, the antenna up the 15-foot mast, there's a chance it might be able to be copied. So the improvement's going to be there. It's not going to be huge. We're not going to have any oh wow moments, but it's generally a move in the right direction. So anytime Judy hears she can get more power, more range, more anything out of her antenna, she says, do it. So I think that's what I'll be doing. So that's kind of my take on how we took a look at this. And, like I said, I'm no antenna guru. Just kind of working my way through this. And so if you have any questions, let me know. More importantly, if I'm missing something or have something wrong, I'd really like to hear about that. So I want to thank you if you made it through this without falling asleep, and say 73. This is K3SKS, and I'm clear.